Good afternoon, everybody, and good evening if you're in Europe, and I guess it's a little past evening if you're in the Far East. It's my great pleasure to welcome you to this semi-plenary lecture by Professor Assad Oberai from University of Southern California. I can say a great deal about Assad, so I'll keep it short and politic here, but Assad's been a long-time friend and, more importantly, colleague for a very long time. Assad obtained his PhD at Stanford around 1998. He began his career, his academic career at Boston University. Pretty soon after that, moved to RPI, and in 2018 to University of Southern California, where he is the Hughes Professor in the Aerospace and Mechanical Engineering Department. He also is a Vice Dean for Research. Speaking of research, Assad's work has spanned really all the important areas of computational mechanics, beginning with acoustics, turbulence modeling, variation of multi-scale methods, inverse problems, and on inverse problems, he's done a lot of really important work in methods aimed at medical detection and diagnosis, and he's done some very important development in elastography, which is an inverse problem. More recently, he's been doing also very insightful, penetrating work in data-driven modeling. That's the name of his group too. It is the Data-Driven Discovery Group in at USC. And there too, of interest to them are methods that again aid detection and diagnosis of cancer, but also go beyond that, thinking about physics based machine learning and machine learning for physics and mechanics, and you can see that already from the title of his talk. He does more, from mathematical work related to graphs and differential equations extracted from graphs to applications such as coming up with good priors. He does them all. We're looking forward to hearing his talk. Oh, and I should just mention that he's very well decorated as well. Among his awards are the ASME Thomas J.R. Hughes Young Investigator Award, the Humboldt Foundation Award for Experienced Researchers, the Barcelona Erasmus Mundus Master Course Lectureship at the Universidad Politécnica de Catalunya. He's also the Fellow of USNCCM, ASME, AIBME, and so many awards. Okay, so I think I've gone over the time I intended to take, but it's a great pleasure, and Assad, all yours now.
Thank you. Thanks, Krishna. Thanks very much. Thanks for the kind introduction. I'm waiting for sort of the screen to transition to my slides. There we go. And I really do want to thank the organizers for this opportunity to talk about some of our work at the interface of computational mechanics and machine learning. This is work that's been done by Dhruv Patel, who's now, used to be my PhD student, is now a Timoshenko Fellow at Stanford University, Deep Ray, who's my postdoc, and Harish Shankar Ramaswamy and Saeed, who are two PhD students working in micro. So let's move right on. And let me just talk a little bit about the theme of today's talk. So really, it's about the interaction between computational mechanics or computational physics and machine learning, and how the two can benefit each other. And this is our take on it. I know there are lots of people working on this and have really clever ideas. So rather than being very broad and expansive, I'm going to be narrow and not so expansive. So in this talk, machine learning will help computational physics by providing tools to solve inverse problems. And computational physics will help machine learning by providing tools for quantifying uncertainty. So that's the theme for today's talk. And in the mix, in the ingredients are sort of three important concepts. One of inverse problems, the other of Bayesian inference, and finally, from machine learning, generative adversarial networks. So that's basically the theme of today's talk. And here is an outline. So I'll spend maybe the first third of this talk talking about these ingredients, how they relate to each other. And then I will, that will include talking about inverse problems, Bayesian inference, and then GANs. And then an important component in Bayesian inference is the prior. And then I'll talk about how GANs can be used as priors. And yet another important component in Bayesian inference is the posterior. And I'll talk about how GANs can be used as the posterior. And then I'll end with some conclusions. In each of these topics, 2 and 3, GANs as priors and posterior, I will also, I'll give you examples where these ideas will benefit computational physics or computational mechanics, but also give you examples where these ideas benefit applications in machine learning. So things like computer vision and medical diagnostics. So that's the plan for today's talk. So let's start with ingredients. And let's start with inverse problems and a famous quote from Joe Keller, which describes what inverse problems are. And roughly speaking, in this article, Joe says that two problems can be considered inverse of one another if the formulation of one involves the solution of the other. So that's basically, that narrows it down to two problems, but which one is inverse and which one is direct? And this definition is rather vague. Basically, what Joe says is the problem that's studied well is the direct problem, and the problem that's not been studied well is the inverse problem. And I think this is a pretty good definition for inverse problems, certainly works for all my applications. And then Joe goes on to give some serious and some not so serious examples of inverse problems. And among the latter is the following. What is the question to which the answer sounds like 9W? Now, in his article, Joe says the answer is, do you spell your name with a V, Herr Wagner? So that's his answer to this inverse problems. But if you attended Joe's talk on this topic, he says, well, there are other equally likely answers. For example, what size shoes do you wear? What is the highway west of the Hudson River connecting New York City to Albany? And so these are also equally likely answers. So this sort of points to sort of, one fundamental problem with inverse problems, and that is they can have multiple solutions. They can be ill-posed, right? So that's a problem with inverse problems. So let's come back to sort of the problems we want to solve, the kind of inverse problems we want to solve. And a typical example is of, where the direct problem is the sort of the forward problem of heat conduction. So given the equation of heat conduction, boundary conditions, heat sources, and conductivity determine temperature. That's the direct problem. The inverse problem is given the equation of heat conduction and temperature determine conductivity. And as I said, inverse problems are riddled with difficulties. They're not well posed. Usually, when you solve an inverse problem, you measure a response. That response is almost always noisy. And then finally, to answer the question, you need context. You need some prior information. And that has to be sort of built into your solution, right? So those are sort of the three problems with inverse problems. And there are roughly two ways of solving them. One is regularization. We won't talk much about it. And the other is Bayesian inference, which is basically saying, let's roll up our sleeves and let's interpret the inverse problem really as a probabilistic problem, and then not only solve it, but also quantify the uncertainty in the solution, right? So that takes us to Bayesian inference. Before we get there, that's the second ingredient. Let's introduce some notation. So in this talk, the parameter that we'll want to infer always is going to be denoted by X, and it will live in some domain omega X, which is going to be a subset of an NX dimensional real space, right? The response will be denoted by Y, which will live in omega Y, which will be a subset of RNY. And there will be a direct map, which will map us from omega X to omega Y. And sometimes we'll assume that the noise in the measurement or the response is additive, and it'll be denoted by eta, and the distribution in the noise will be denoted by p eta. So that's notation. Let's move on to the second ingredient of today's talk, which is Bayesian inference. So Bayesian inference sort of stems from Bayes' theorem, which is nothing but a restatement of the definition of the conditional distribution. So the joint distribution, the conditional distribution of X conditioned on Y is nothing but the joint distribution of X and Y divided by the marginal distribution of Y. But given that, I can replace the joint distribution in the numerator up here with the conditional distribution of P of Y given X times the marginal of X. And this basically, the left-hand side here and the right-hand side here is Bayes' theorem. Now, when using Bayes' theorem to solve inverse problems, we sort of interpret it slightly differently. So we think of the information that we know about X, the parameter we want to infer, before a measurement and after a measurement. So what we do in this formula is we replace this marginal with the prior information that we know about X. So the prior distribution comes here. We replace this conditional P of Y given X by the likelihood function, which for additive noise looks like this. and the direct map comes in here. And then what we get out of this is what we know after the measurement, and that's the condition, that's the distribution for X conditioned on the Y, on the measurement or on the response of the system. So that's the formula that appears in Bayesian inference, right? And so the question is, how do we apply this formula? So that's given here. So I've rewritten the formula here, and the way this would work is the very first step in Bayesian inference would be to construct a prior, will be to construct a distribution that captures all the prior information about the map you want to infer. And then after that, you apply this formula. So for a given measurement Y or a given response Y, for any X, I can substitute the X in these two terms, and I can evaluate this quantity, which is proportional to the distribution, right? And then by doing this for multiple X's, I can use a Markov chain Monte Carlo method to actually approximate the posterior distribution P of X given Y, which is basically the solution that I'm looking for. So that's the way this is going to work. Step one is, construct a prior. Step two is use this formula and use Markov chain Monte Carlo. Now there's a problem in doing this, and there are actually two major problems in doing this. The first problem is when the dimension of X is large, so when NX is large, sampling using Markov chain Monte Carlo or even training Markov chain Monte Carlo methods is very, very hard. And this is the so-called curse of dimensionality. And the second problem is how to construct informative or useful priors. And what do I mean by that? So a typical prior that gets used all the time is a Gaussian prior, which basically says heavily penalize large values of X, right? That's what this is. The probability is going to be large, is going to be very small for large values of X and large otherwise, something like this. But your prior information may be nothing like that. It might actually be a microstructure, and four of whose samples are shown here, or it might be some natural image. In this case, this is the MNIST database, and it might look like this, or it might be some medical image. In this case, this is MR scan of the brain, and you want to encode this as a prior. So how would you do that, right? So that's a question we're trying to address. And so that brings us to the third ingredient of today's talk, and that is generative adversarial networks. So these were introduced by Goodfellow a while ago, well, maybe let's say about 78 years ago. And the way to think about them is you give me a lot of samples from a distribution, and a GAN will learn that distribution and will provide an effective way to sample from that distribution. So a GAN comprises of two components, a generator and a critic, right? Both of these are deep neural networks. The input to the generator is this vector Z, which lives in what is called the latent space of dimension R and Z, and it's sampled from a very simple distribution, usually Gaussian or something like that. And the whole point here is that the number of the dimension of this latent space is much smaller than the dimension of the output of the generator. So you take a Z, you push it through this deep neural network, and you get something on the other end, and this lives in R and X in omega X, and the dimension of that is much bigger than the dimension of this. So that's the generator. Then there is the critic, which takes entities that live in omega X and maps them to the real line. And it takes two types of entities, one that are produced by the generator, another which are sampled from PX. And the weights of this generator are determined so that you get a large output whenever X is sampled from PX, and you get a small output whenever X is sampled from PX down here, and a small output whenever it's sampled from the generator, right? Whereas the generator sort of tries to do the opposite. So let's construct a loss function that'll do this. And so this is the typical loss function that's used in a Wasserstein GAN. So what you do is you take the output of the generator, the discriminator, where you feed it all the X belonging to the true distribution. So you take the expectation of that, and then with the negative sign, the expectation of all the Z's that are sampled from PZ and pass through the generator. And so a discriminator will try and maximize this quantity. So you'll determine the weights of the discriminator by maximizing this, whereas the generator will try and minimize this under some Lipschitz constraint on the discriminator. When you start doing this, you can show that the optimal generator, right, it'll converge to something, and that something will have the following property. So if you measure the distance between px, the true distribution, the Wasserstein distance in particular, and the push forward of the generator of the distribution of the latent space, that quantity is minimized by the optimal generator, meaning thereby that these two distributions are close in a particular metric, in particular the Wasserstein 1 distance. And convergence in W1 implies weak convergence. So what that means is if I take my x, sample from px, and compute some nonlinear function m of x and take the expectation of that, that's the same thing as sampling z from pz, pushing it through the optimal generator, computing the same nonlinear function and computing the average of that, right? So that's the weak convergence of a Wasserstein GAN that we'll make use of. Here are some examples. These are dated. These are about 3 years old that a Wasserstein GAN can produce. So down below here in the lower 3 rows are images of true celebrities. And these were used to train a Wasserstein GAN. And each image contained about 3 million different real numbers. And these were sort of mapped to the latent space of a GAN, which is only 512. And then that was used to produce these fake images that appear in the top row. Since then, there are lots more impressive examples. This is, like I said, a little bit dated. All right, so those are the 3 ingredients: inverse problems, Bayesian inference, and GANs. So now let's start putting them together. And the first thing that I'll talk about is using GANs as priors to solve Bayesian inference. Okay, so here we go. So let me set up the exact problem that we want to solve. So let's assume that we are given lots of samples of X, the field that we actually want to infer, right? So a priori, I've given you lots of samples of what X could look like, right? Sample from PX prior. I also give you the direct map, f of X, and let's assume additive noise. So I give you the distribution for noise, and I give you one measured response, right? You measure the response somewhere, and I give you that. And what we wish to determine is the posterior distribution PX post, right? So we want to solve this Bayesian inference problem. So how would you use a GAN to do that? So in the first step, what we do is we take this set S and train a GAN, and we get an optimal generator G star. And then using the convergence formula that I described in the previous page and the definition of what a posterior is, in 2 or 3 steps, you can show that computing the expectation of any nonlinear function of X sampled from the posterior of X is the same as computing the same nonlinear function of G star of Z, right, where G is the optimal generator, and Z is sampled not from PZ, not from the original distribution that you started out in the latent space, but actually a posterior analog of that, which is given here, right? So this is basically, you could say, the pushback to the latent space of the posterior distribution. And the whole point here is we've taken the sampling problem, which was sampling in X, and reduced it to sampling problem in Z with a posterior distribution that is defined purely in terms of quantities that involve Z. And so that's the dimension reduction that you've achieved. And so the second step will be to in this algorithm will be to use this formula. So I'm going to skip back, pardon the whiplash. So use this formula, and then for every Z, you see that I can calculate PZ post up to a multiplicative constant. So then I can generate a Markov Monte Carlo, a Markov chain Monte Carlo approximation to this posterior distribution in the latent space. And then once I have that, I can sample from that. So I sample Z from that chain, and then I push it through the generator and then through the nonlinear function that I want to compute divided by the number of samples. And that's an approximation to the posterior, or the same thing that I was trying to compute over the posterior, right? And so that's basically the algorithm. So 3 steps. First, train the GAN. Second step, generate this Markov chain Monte Carlo approximation. And third step, sample from this chain. And what have we achieved in doing this? What we've achieved in doing this is the ability to represent complex priors that are learned from the data set itself, and the fact that we've reduced the dimensioning or the sampling problem from NX, which can be large, to NZ, which is hopefully smaller. So we've achieved dimension reduction also. All right, so let's see how this works. So the first few examples I will give you are these ideas applied to computational physics. And then the same thing, but now applied to computer vision. Okay, so the first problem, let's say we want to solve, is the one I introduced right at the beginning. So the inverse heat conduction problem. So this is, this is basically the constraint, the PDE constraint. So kappa here is the conductivity, U is the temperature, heat is the heat, H are the heat sources. What we're going to do is represent U, which is the temperature, which is the response, through a vector Y. So this is my response vector. The nodal values of U are my response vector, and the nodal values of kappa are the parameter that I'd like to infer, right? So the problem we are solving here is, given a noisy measurement of temperature, can you predict what the thermal conductivity is going to look like? I'm not interested in just one answer. I want to characterize the entire distribution of possible thermal conductivities. That's what we're trying to do. And in this case, we need the forward map, and the forward map was implemented in Phoenix, and we assume a really simple model for noise in this case. All right, so let's, now that we've set up the problem, let's solve it. We're going to solve it for 3 different priors, just to show you how this method can actually work. So remember, the first step is to learn the prior, right? So in this case, we construct a prior so that we can actually test our answer. So our prior can be represented on a very low dimensional manifold. In this case, just 4 dimensions. So we assume that the conductivity is in the form of a rectangular inclusion that is parameterized by the coordinates of the bottom left and the top right corner, and it varies linearly in between. So those are the 4 parameters, right? So these are 4 samples on the left that are the true samples. We use this to train a GAN whose latent space is 5-dimensional, and it generates samples that look like this. So we're convinced, it is converged, and hopefully learn the distribution, the prior distribution that it was supposed to learn. And then we can start testing it, right? So this is purely a validation, right? So we take a true conductivity field, which looks like this. This is not, the GAN has never seen this conductivity field. The GAN used to train the prior. We solve the forward problem. We get a temperature which looks like this on the bottom, on the left hand column of the first row. Add a whole lot of noise to it, right? And then, given this measurement, we try and predict the posterior. Since this case has a low dimensional representation, right, just 4 dimensions, we can actually use Monte Carlo to calculate the true statistics. So the true mean looks like this. The true standard deviation of the inferred conductivity field looks like this. And what we've shown here on the right now, these 3 columns are the statistics generated by the approach that I talked about. So this is the map. This should be, or the maximum a posteriori estimate. This should be compared with the true field. The mean, which should be compared with the true mean, and the standard deviation, which should be compared with the true standard deviation. The row below is for a different measurement, but is pretty much the same thing. So this sort of gives us confidence in that fact that this approach is working. We can now tackle maybe more complicated problems. So here is a representation of thermal conductivity in the form of, let's say, MNIST digits, right? So hand-drawn digits. In this case, the parameter space for X, the quantity we want to infer, which is basically the nodal value of the thermal conductivity, is 784. We train a GAN, which has a latent space of about 100. So this is a reduction of a factor of 7.8, right? And these are the 4 samples that are chosen, let's say, from the true set. You use maybe, I think we used about 10,000 such samples to train the GAN. These are the samples generated by the GAN. Once we are convinced that the GAN algorithm has converged, we then solve the inference problem. So using that as prior, we solve the problem of inferring the thermal conductivity. So here is the true thermal conductivity, the digit 4. We solve, the heat conduction problem corresponding to this, which gives us a temperature which looks like this. we add noise to it, and then use the GAN approach to compute the most likely answer, the map, which matches the true conductivity quite well. Also the mean, which looks like the map, but if you look closely, the boundaries are sort of fuzzy. The standard deviation, so this is telling us where the uncertainty is. And in this case, the uncertainty is at the interface of these digits. So that's where we are most uncertain about our prediction. And then as comparison, we compare with a total variation reconstruction of this inverse problem, which basically looks, not so good. So this prior, this really strong prior, has helped us in getting a really accurate solution. We repeat this experiment with the digit 7, but now in the temperature field, this measurement field, we occlude a significant portion of the measurement, and we are still able to perform really well, again, because of a strong prior in this case. Moving on, so a more sort of a, let's say, an engineering type solution here. So here we look at lots of images of a microstructure that is obtained by solving the Allen-Kahn equation corresponding to different random initial conditions, and 4 such distributions of, let's say, thermal conductivity are shown here. We use about, I think we used, again, about 10,000 such to train the GAN. In this case, the omega x, which is the space, the dimension of space of x, was 64 by 64 pixels, so about 4,000, but the latent space of the GAN was still 100. So this is a reduction of about a factor of 40, so a significant reduction here. These are the samples produced by the GAN. Once again, we apply our approach. We start with a true distribution, which looks like this, solve the thermal conductivity, solve the heat conduction problem, get a temperature, which looks like this, add noise to it. And so this is our measurement, and solve the inverse problem. And this is the most likely approximation. So now this is where things get interesting. Notice that we, in solving the forward problem, we employed 0 temperature boundary conditions along these edges, all right? If you look at the map does a really good job in the interior, but in the corners, there is a significant difference between the map and the true distribution, right? And why is that? Well, that's because in the corners, the temperature distribution is determined by the boundary condition and not really by the conductivity. So what happens is our reconstruction is not very sure of what it produces in the corners, and often the most likely guess, not often in this case, the most likely guess is wrong. But if you look at the mean, you will see that it's fuzzy in these regions. And if you look at the standard deviation, what you will see is it is peaked exactly in the places where the answer is uncertain and actually the map is wrong. So this is where uncertainty is telling us that, please don't trust that answer too much, because I simply don't have enough information to make a confident prediction, right? So this is sort of like the true utility of doing UQ on problems like these. Okay, I'm going to skip this problem on the radon transform and now talk a little bit about how these ideas can actually help applications in machine learning. So there are 2 applications that I'll talk about here. One is classification, so given an image, tell what its label is. The other is in painting, which is given an image, you take out a part of it and you ask someone to fill in what was taken out, right? And there are 2 particular things I want to talk about. One is, can we use UQ to detect out of distribution samples? So often machine learning algorithms will produce an answer and will be very confident of that answer, but will be wrong. However, if you do UQ correctly, they should not be very confident of that answer. So that is, can you detect a sample that you've never been trained on so that you can tell the user, please don't trust my prediction. And the other part, other application is active learning. Okay, so in order to apply this approach, the approach that I talked about earlier, one has to think about what the direct map is in this case, because there is no physics-based phenomena here. And so the way to think about it is, if I look at classification, I look at, Y is the noisy image, so that's my measurement. X is the label, what I want to predict. I can combine these 2 and produce something that I call U, right? And then my direct map simply becomes the restriction operator R applied to U. So that stands in for a direct map. Now, given that, I can then apply all the methodology that I talked about earlier to do UQ on these types of problems. So let me quickly sort of just give you an example of what that looks like. So this is from image classification, right? So once again, we train a GAN, but in this case, we train it not just using the images, but their labels also, right? And we use the MNIST data set of handwritten digits, which looks like this. And once the GAN is trained, we show it a noisy image, right? And then apply our approach to calculate the distribution not only for X for the label, but also the distribution for a Y, because we produce a distribution for U, which includes X and Y. So using the distribution of X, we can compute the most likely answer for the label, and that was, gives us 98% accuracy. That's fine. But then what we can do is we can use the distribution that we get for Y to find out whether the input was out of distribution, was something that this algorithm has never seen before, or something that it has seen before. So what we do is we compute the distance between the response and the measurement and our most likely guess. If that distance is large, then this algorithm has never seen this particular sample. If that distance is small, then it has seen this sample. So that way we can detect whether it's out of distribution or not. And so in this case, we show it MNIST, which is this, and we get we get a histogram which is of basically of values of these, which is very, very large, whereas for MNIST we get very small values. So this is a good way to sort of tell apart what's going on. Another place, like I said, where you can use these ideas is in active learning. Okay, so this is basically sensor placement. So here, we apply this approach to do image in painting, like I was telling you. We train a GAN on the Celeb A data set, and then we say, okay, if we show you a portion of that image, can you predict what the distribution of the rest of the image, in fact, the entire image looks like, right? So we show nothing first. That's what this white square means. And we, of course, we do predict the most likely answer, which means nothing at all. We predict a mean and we predict a variance, right? Now, wherever the variance is higher, we select a square tile and we open up a sensor there and we measure that part. Now, using this, once again, we predict the most likely estimate, the mean and the variance. Again, nothing useful here, but the variance is larger here. So we open up another tile and we get these two. We keep doing this. And then in the end, by opening 7 or 8 tiles, we can get a guess to the face here, which is quite close to the actual image that's being used here, right? So this is where we're sort of using active learning or design of experiment, if you will, placing the sensors wherever the variance was largest to get to the answer as quickly as possible. All right. So this was, again, so this is sort of ideas from uncertainty quantification being applied to machine learning. Let me sort of move over and move on to the last part of the talk, which talks about using GANs as approximations to the posterior of a distribution rather than a prior. So this is basically work that builds on the work of Adler and a couple of other people. I've listed the references there, and I don't have sort of time to get into how different it is, but I'll still try and do that later. Okay, so here the tool instead of a GAN is a conditional GAN, and the conditional GAN works sort of like the traditional GAN. So you have a latent space Z, you sample from that latent space, and its dimension is much smaller than the dimension of the space X. But in addition, you have another space, which is, or you have another input, which basically lives in the space of measurements, and they go into the generator, and the generator produces something that lives in the space of the parameter that you want to infer, right? So that's that. You come over to the critic or the discriminator. So the discriminator takes these pairs. So it takes X and Y and maps them to a real number. And it takes 2 sets of pairs, one which are sampled from the true distribution of X and Y, the joint distribution of X and Y, and the other where the Y is sampled from the true distribution, but the X is generated by the generator, right? And now if you sort of, absorbed what I said about the previous GAN, what the conditional GAN discriminator will try and do is for the X and Y pair sample from the two distribution, it will try and maximize this expectation, and it will, and for the pair where Y is sampled from the two distribution, but X comes from G of Z, where Z is sampled from PZ, it will try and minimize this. So you put a negative sign in front of it, and you say that the critic or the discriminator will try and maximize this, right? Whereas with the Lipschitz constraint, whereas the generator will try and minimize this. So you get a min-max problem. And then once again, sort of going through the same steps, you can prove that the optimal generator will be the one which minimizes the Wasserstein-1 distance between, this is the critical part, the distribution of X given Y, right? And the push forward of PZ by the generator, right? So what the generator is learning here is the conditional distribution of P of X given Y. And since, again, convergence in the Wasserstein metric or the Wasserstein distance implies weak convergence, what this means is if I wanted to compute some nonlinear function of X and over the conditional distribution P of X given Y, I could do that by simply sampling Z from PZ, pushing it through the fully trained generator, then computing M of that, and then taking the expectation of that, right? So you can see right away that this has got to play an important role in approximating the posterior. And that's what this slide tells you. There's nothing much really here. So basically, let me set up the problem that it can be used to solve and then tell you how we solve it, right? The problem that it can solve is you need a set S which contains X drawn from the prior, and then you need Y's which are conditioned on each of these X's. So you need to be able to generate this. So that's what you need. And then of course you need one noisy measurement where you want to say you want to now infer the X corresponding to this, right? And the way to do this is you train now a conditional GAN, right? And let its optimal generator be denoted by G star. Then using the statement of weak convergence that I just showed you in the previous slide, and again, the definition of what a posterior is from Bayesian inference, you can say that, computing the expectation of M of X for X sample from the posterior is exactly the same as the expectation of Z sample from PZ, the original distribution in the latent space, right? And pushing it through the generator for a given Y and then computing the same nonlinear function, right? So this again becomes a really simple sampling problem. So in step 2, what you will do is simply take samples from that generator. So there is no Markov chain involved here, push it through this conditional GAN, and then compute this statistic that you're interested in. So there are only 2 steps. So the gains, once again, are that you can represent complex priors. Once again, you've done dimension reduction. In this case, an additional gain is there's no Markov chain Monte Carlo involved. You can simply sample from Z and you're done. So I'll come back to how, so this is work that's been done by Adler and lots of other people. What we've done slightly differently is we have sort of focused on the map that takes you from Y to X and realized a particular structure called the unit structure, which is basically like a multi-grid structure, which works really well because it allows you to sort of impose locality in the spatial domain in that map. And then we've also used this idea of conditional normalization, which allows uncertainty at multiple scales. So let me show you a few examples, actually just one example, one from physics, physics-based applications, the other from computer vision of how this approach works. And that will sort of take me to the end of the talk. Okay, so we've seen this problem before. It's the inverse heat conduction problem once again. And what we want to infer is X, the nodal values of the thermal conductivity. What we are given is Y, the temperature field. But now in order to train our GAN, the very first step of this approach, we need to establish a prior for X. That's completely up to us. Solve a bunch of forward problems and then get the corresponding Y and then use that to train the GAN. So that's what we do here. So these are each of these are a pairwise sample that was used to train the GAN. So there are 6 samples here. And you can see as a prior, we chose a circular inclusion of some contrast located at somewhere uniformly distributed values of the center and having a certain diameter and, and some contrast, right? So that's our prior. And then for each case, we solve the forward problem, add noise to it. And so you can see the temperature field corresponding to each of these circular inclusions. And then we train our conditional GAN, right? And then we solve the inference problems for circular inclusions here. So the target is this circular inclusion, right? This is the noisy measurement. And then we use this to, in the conditional GAN, once it's fully trained, so that's the Y, that's the input that goes in there, then we sample over Z and then compute statistics. So these are the statistics. This is the mean, this is the map, and this is the difference between, this is roughly the error, you could say, in our reconstruction, and this is the standard deviation, which is saying that it is most uncertain about where the boundary is, and it is more uncertain wherever the conductivity is high, which makes sense because the change in temperature corresponding to change in conductivity is smaller in regions of higher conductivity. So the signal is much smaller there. So your uncertainty should also be larger there, right? And this is another example in the second row. The third row is yet another example. So that's great. It's working well here, and that's exciting. But what we said was, what if we try and extend this a little bit? In particular, what if we gave it something that it hadn't seen before? So as target now, we took two circular inclusions in the same field and generated the temperature corresponding to that, and then gave this to this conditional GAN and asked it to produce the conductivity field, right? And what we found here was, to our surprise, it actually did produce two inclusions. It wasn't as good as it was with one inclusion, but it did produce two inclusions in the mean, in the mode, and even in the standard deviation, showing it's uncertain there. So this was a little confusing to us. So then we said, okay, let's bring these inclusions closer together. So this was the target here. And now it did produce the second inclusion, but not so well. And then we brought it even closer. And then after a while, the second inclusion sort of went away, right? So there was some generalizability that was going on here. And I'm going to sort of come to the punchline in the next slide. So then we said, let's just take, again, the same conditional GAN, which has only seen circles, but now show it ellipses, right? So the target is ellipse. Here is the measurement, and this is the mean and the mode that it produces. And, it does its best to produce an ellipse, but it basically circularizes the ellipse, right? So it stretches out its minor axis so that it looks more like an ellipse. Here is another test, and it tries to make it look like a circle. But if it really does look more or less like a circle, of course, it does a really good job. So the question really was, we are seeing some generalizability. And the other thing, we know that there is no magic. So why did we get this? Why was it able to do this type of generalizability in a way that made sense? And what we've concluded is it's because of the architecture of the UNet. Basically, I told you that it controls the locality of the map between Y and X, right? So what our conclusion was, in this particular case, our unit architecture was such that it learned the local map, or roughly speaking, the local plus some sort of a neighborhood map between temperature and thermal conductivity, and then kept applying it multiple times. So as long as things were separated apart, it was able to do well. And of course, as we brought those two inclusions together, then it could not distinguish them from each other because it had never seen anything like that before. So I think I'm running out of time.
We're about 7 or 8 minutes from
okay.
the end. And I should just mention very quickly that for listeners and the audience, if you can type your question into this little box which says "Ask a question to the speaker," that would be great. We'll relay them to us.
Okay. Right. And then, so this brings me to my last example. And so now this is basically these ideas, but now applied to computer vision in a problem that is referred to as brain extraction problem, which is not as invasive as it sounds. basically, it's like you're given an MRI slice of the skull and the meninges and the brain, and what you want to do is extract just the pixels that correspond to the brain from that, right? So you go from here to here, here to here, here to here. And the tough thing here becomes when you're dealing with an image like this, where you also have, let's say, the eye sockets, and it's challenging to sort of do that extraction. So we did this, right? So measurement in our case was the MR slice, and the output was the brain extracted from the MR slice. And so let me just show you some examples. So this is a slice that's taken, this is the input from the top of the brain, like from somewhere here. So you can see that the meninges actually, because it's something that cuts through like this, you get a larger cross-section of the meninges, but the brain is this small thing here. This is the target. This is what the algorithm will produce. You come down a little bit here. The meninges become, or the section has very little of the skull and the meninges, and the brain is actually pretty easy to extract. And that works. And then you come down to the level of, in this case, the nasal cavity. And the brain, in this case, is actually 3 different parts. So this is the target. And once again, this algorithm is able to produce a pretty good answer, including the variance. Now, this is where it is actually really useful, which is quantifying uncertainty. So in one of these examples, like right here, what happened is the algorithm incorrectly assumed that this part of this, I think what is the meninges, is actually the brain, and where the target obviously did not have that. But it also produced a large value of standard deviation here, telling sort of the clinical practitioner, please don't trust this too much, or have another look at it and see if it makes sense. So that's all I'm going to say. I will sort of maybe make a quick comparison for the 2 approaches that I talked about, GANs as priors and GANs as posteriors. I feel like in general, you can look at them as, what kind of training data they required, whether they require a forward model or not. Is the sampling easy or hard? And generally, is it possible to control generalizability, right? And I feel like sort of the GANs for posterior approach comes out ahead in 3 out of those 4 cases. I'm going to leave the conclusions up there, acknowledge support from all these agencies, and take time to answer questions, I guess, Krishna. Thank you.
Thanks very much, Assad. That's very comprehensive and deep. So like I said, please ask, put questions into the little box that you see there. I have a couple of questions, so while you're warming up, while the audience is warming up, I can ask my questions maybe. So going back to where you're combining active learning to do the do the in-painting problem. You start out with essentially a blank label, and then is the map.
Right.
Right. So this is with the face with the images.
Right. Sorry, which one were you talking about?
Yeah. This one. I think yes.
Yeah.
Correct. Right. Absolutely. So you start out with something that's blank, and it just produces. Then it gives you back the map, which is essentially what it would give you if you had not. Okay.
Yeah. So that's basically it's just the prior, right? So the there is no the likelihood term is uniform. And so the prior will have a mode somewhere, and so this corresponds to that. And so that's what it's producing, but of course it's completely uninformed.
Oh, I see.
Because there is no measurement, right?
Right.
But you can still compute statistics, and you can compute the variance. So this is basically down here is the variance of the prior itself. And you can see that what this is telling you is that that's where the images were most different from each other.
Okay, and this is just the baked in variance in the prior, which it then goes off.
Exactly.
Okay.
Only the very first one, right? The moment you open up this tile in the second one, now the likelihood comes in, and things start to become different. So, for example, if you look at the second column and scroll down, what was initially very bright, that top right circle has now become dark, so the variance has gone down there, right? Because you nailed that. And then you keep doing that, and you can nail variance. So I guess this is a kind of a simple way of showing that if you know where you're most uncertain, you can place the sensors there and sort of in an optimal way get to sort of the guess that will have least uncertainty.
Cool. Okay.
That's what this was doing.
So, all right. There are a couple of other questions. Let me start with actually quite a few while I was asking mine. Okay, let me see if I can get through some of them. From Miguel Besa says, "Thank you, Assad, for your talk. GANs can be quite tricky to train for complex problems. Have you encountered practical difficulties in training for these inverse problems? If yes, can you elaborate on what happened and how did you alleviate the issues?"
Yeah, that's a really good point from Miguel. So yes, we have, and we've spent quite a bit of time sort of thinking and learning about best practices in training GAN. So here's what I would say. I've always found the Wasserstein GAN to be sort of the most robust. So we almost always work with Wasserstein GANs. And now within Wasserstein GANs, there are different ways of enforcing the Lipschitz 1 constraint. And so we use what is called the gradient penalty approach. That also helps with robustness. And then finally, I would also say that there is another approach called spectral normalization, again, to help with enforcing the Lipschitz 1 constraint. And that also helps. Finally, I would also say that keeping track of the Wasserstein distance as reported by the discriminator is a good idea as you're marching through the epochs, because we've almost always found that once that stabilizes, you've pretty much reached an optima that you don't need to go any further. And then finally, I would say this, that sort of experimenting with the latent space is almost a must. So maybe you can do it in decades so that you don't have to do too much training, but you could start with a latent space of 10, then maybe go to 30 or maybe 100 itself, and then maybe think about 500. But do that because a priori you don't know the inherent dimension of the data that's given to you, right? There are ways of extracting that, and if you were sort of smart enough to do that, by all means do that. But then, certainly try and play with that also.
Okay. I'm being told that we're over time, but let me see if I can slip in one more question and maybe you can very targeted answer. Okay, Tuhin Roy, thank you, Dr. Oberai. Very nice and informative presentation. Quick question regarding noise distribution. You mentioned IID. So my question is, if it's not the same, if it's not the case, especially if the noise does not follow the IID assumption, then will the GAN work without IID?
Yeah,
noise
good question.
IID.
Yeah, so I think we've experimented with that in both our approaches, where we use GANs as priors and GANs as posteriors. Now, GANs as posteriors, no problem, because it learns the map from Y to X, and it also learns the noise, right? It's mapping Z to X also. So whatever it is, it'll do its best to learn that noise. Now, GANs as prior, it is an assumption that we've almost always made, and it seems to be robust enough that it gives us reasonable answers. And I'm going to stop there.
Okay. Okay, there are a couple of more questions from Susanta Ghosh. I'll just mention it, and I will, maybe Susanta, you can follow up with Assad later. It says, great talk. Please comment on the vulnerability to the degree of noise in the measurement, sort of similar. Instance, standard PD constrained optimization problems for ultrasound elastography are susceptible to large noise.
Yeah, it's a really good, so I think, of course, it is susceptible to noise, but I think if you have a strong prior, you can use that to compensate for the likelihood doesn't buy you.
Great. Thanks, Assad. I do have a question, but maybe I'll ask after we go off the air so we can keep things moving along. Thank you, Terry. Thank you very much again. Like I said, great talk. As you can see, the questions were coming in, and we'll probably get a few more pings and requests. Okay, great. Thanks, everybody. And we'll sign off